Hello everyone, my name is Tanuja Khan, Assistant Professor, Department of Education, the Bhopal School of Social Sciences, Bhopal. This is a sequential lecture of statistics. In this lecture, we are going to discuss about Anova, that is analysis of variance. In this lecture, we are going to cover about the introduction of Anova, assumption and application of Anova, techniques of Anova and the classification of Anova with the help of working rule and examples. To test the significance difference between the two samples, we generally use t-test and chi-square, but this approach is not applicable, is not appropriate for testing the significant difference between more than two samples. Anova is originated by Ronald A. Fisher in 1923 and further developed by George M. So, the main objective of using Anova is to find out the significance difference between more than two samples. Anova works with total variance. Total variance is the combination of variance between the samples and variance within the sample. Now, moving forward, for the assumptions of Anova, there are three major assumptions which we follow in Anova. The first one is normality. Now, normality, as we know that Anova is a parametric test. So, population from which the sample has been selected should be normally distributed. The second assumption is independence. Here independence means sample are independent from each other. The third assumption of Anova is additive property. Here additive property means variance of various component must be equal to the total variance. Now the next part is the application of Anova. The first application is to test the significant difference between the means of more than two samples. The second application for analysis of variance is to test the significant difference between the variances. The third assumption is to test the significance of correlation and regression. Anova's classification. Anova basically divided into two categories, two classification. The first one is one-way classification and the another one is two-way classification. One-way classification is generally used only for one independent variable with generally three or more than three levels of the samples. Working rules for Anova. To solve any Anova problem, there are majorly 7 steps which we follow during the solution of the problem. The first one is the formation of hypothesis. The second one, to find out the total of the sample items. The third one is to find out the correction factor from the given data. The fourth one is to find out the total sum of squares, that is also denoted with SST. The fifth step is to find out the sum of squares between the sample, that is known as SSB. And the sixth, the second last step of Anova is the sum of squares within the samples, that is denoted by SSW. The last and very important step of Anova is to draw a table of Anova analysis and interpret the data as per the findings. Let me explore all the working rules steps with the help of one example. Now here's the example. The following tables give the yield of 4 plots, each of 4 varieties of rice. Find out that the variety differences are significant or not at 5% level of significance. Here table value is also given at 5% level of significance with degree of freedom 3 and 12, and that is 5.95. We have 4 varieties of rice, that is A, B, C, D in a given data. Now, as we already discussed about the working rule, the first rule was formation of hypothesis, and here for this example we are forming a null hypothesis, that is there is no significant difference in the 4 varieties of rice. Now the second rule is to find out the total of all the sample items. Now we have altogether 16 items in 4 varieties of rice. So our second step to sum of all the sample items. Now for example, we have a first variety that is x1 and the total of x1 is 36. Now the second variety is x2. We are denoting the second variety B that is from x2 and the total of that x2 is 40. The third one, the third variety of rice, the total of the third variety of rice is 48 and the fourth variety of rice is 36. Now the total of sample items that we have already 4 items, we have 4 varieties of rices, that is x1, x2, x3 and x4. Now in the second step, in second working rule, we have to find out the total of sum of all the sample items. So, and that is denoted by T. So the T is equal to summation of x1 plus summation of x2 plus summation of x3 plus summation of x4. So T is equal to 36 plus 40 plus 48 plus 52, that is 176. So our T is 176. With the help of this T, we further find out the correction factor, that is our third working rule. So correction factor, formula for the correction factor is T square divided by N. Now we already know from the second step that our T is 176. So correction factor is equal to 176 square divided by 16. Then we get 30,976 divided by 16, which becomes 1936. So this is our correction factor, 1936. Now the fourth step. Fourth step of working rule is to find out the sum of squares of all the sample items. For that, we have to square each and every sample item and then add it. Now the sum of square for variety number 1, this is summation of x1 square 328, summation of x2 square is 406, summation of x3 square is 632 and the final summation of x4 square is 696. Now the formula for SST. Formula for SST is SST is equal to summation of x1 square plus summation of x2 square plus summation of x3 square summation of x4 square minus correction factor. So this is the formula for SST. Now SST is equal to summation. What is the summation of x1 square? x1 square is 328. So 328. Then summation of x2 square. Summation of x2 square is 406. Summation of x3 square, that is 632. And summation of x4 square, that is 696. Minus of correction factor. So our correction factor was 1936. So put 1936 in place of correction factor. Now sum total of 328, 406, 632 and 696 is 2062 minus correction factor, that is 1936. So the answer is 126. So our SST is 126. Now the next working rule is to find out SSB, that is sum of squares between the samples. Now for sum of squares between the sample, we have formula SSB is equal to summation of x1 whole square divided by n1, where n1 is the number of samples in first group, plus summation of x2 whole square divided by n2 plus summation of x3 square divided by n3, and the last is summation of x4 square divided by n4 minus correction factor. So this is the formula for SSB, that is sum of squares between the samples. Now put all the values in this formula. So from the previous data we know that sum total of x1 is 36. So 36 whole square divided by 4, because we have 4 sample items in first variety of rice. Now the second total, that is summation of x2 is 40. So 40 square divided by again 4, because we have equal number of sample items in each variety of rice. Now the third one is summation of x3, and summation of x3 is 48. So 48 square divided by n3, that is 4, and the last one is also 36. So 36 whole square divided by 4 minus correction factor, and our correction factor is 1936. Now we see 1 by 4 is common in all. So we take 1 by 4 as common. So 1 by 4, now add all the numerators, that is 1296, 1600, 2304 and 2704. So it becomes 7904 minus of correction factor, that is 1936. So now the last we get 1976 minus 1936, that is 40. So our SSB is 40. Now moving ahead for the second last step, that is sum of squares within the sample, SSW. The formula for SSW is SST minus SSB. We already got the value of SST and SSB. So our SST was 126 and SSB was 40. So after subtracting 40 from 126, we get 86. So our SSW is 86. Now what values we have? We have SST, we have SSB and we have SSW. With the help of all these values, we draw a table that is known as Anova table. Now this is the final step, Anova table, from which we will be able to find out the value of F ratio, that is F variance. Now the heading for the Anova table is sources of variation, sum of squares, that is SSB and SSW, degree of freedom, variances and F ratio. Sources of variations are within the sample and between the sample, and we have both the values. So between the sample, sum of squares between the sample, that is SSB, is 40. Within the sample we have SSW also, and SSW is 86. Now degree of freedom is what? It is K minus 1, where K is the number of varieties of rice. In our question we have 4 varieties of rice. So K is 4 in our case. So V1 is 4 minus 1, that is 3. Now for V2, that is second degree of freedom for the entire sample size, that is N minus K. We know that K is the number of groups, that is variety of rice, but here N is the total sample items for entire problem. Now mean variance. The second last column is for mean variance. So for mean variance, for between the sample, the mean variance formula is SSB divided by V1, that is first degree of freedom. So when you are going to divide 40 by 3, then it will get 13.33. So our first mean square value for between the sample is 13.33. Now the for second, that is for within the sample. So for mean square value within the sample is 7.17. This we get from dividing 86 from 12. That means SSW divided by the second degree of freedom. Now the final one, that is F value. F value is a ratio between mean square of between the sample and mean square of within the sample. F is equal to MSB divided by MSW. So our MSB is 13.33 and MSW is 7.17. So our F value is 13.33 divided by 7.17, that is 1.86. This 1.86 is our calculated value, which we calculated from the given data. Now the last but not the least, the interpretation, the result, what we are going to interpret from that F value. So our F value is 1.86. Our calculated value is 1.86, and in the question we already have a table value at 5% level of significance with degree of freedom 4 and 12. This is 5.95, and it is a rule of testing of hypothesis that when your calculated value is greater than the table value, then your hypothesis is rejected. But in our case, our calculated value is less than the table value, because our calculated value is 1.86, whereas the table value at 5% level of significance with the degree of freedom 3 and 12 is 5.95. So our null hypothesis, which we formulated at the beginning, is in this case is not rejected. So the null hypothesis is not rejected, therefore there is no significant difference in the varieties of rise.